Okay, so at 5%, so meaning which one is the highest composition at this point? Regardless of temperature, we have 5% of what? Of tin, isn't it? Yes? I'm just giving an illustration. We can pick any number. So I'll start with 5 because I want to talk about this. So this phase here means it's solid, isn't it? So meaning this, at this particular point, this composition, the alloy, regardless of the temperature, will be in which state? In the solid state. Have you seen that? Is it connecting at the top there? Connecting, okay. Like that, isn't it? But when it goes beyond that temperature, that's when it goes into which phase? You share that one? Actually, I had a copy, I just don't know why I put mine. So it will go into the liquid state, isn't it? Let's say 400 degrees. It will be in which state? In which phase? The liquid phase, isn't it? But up to like 350 somewhere there, let's assume this is true. Or 327, now they've given us 327. Up to 327 to be in solid state. Beyond 327, 328, it goes to what? Liquids. Even the transitional boundary will not happen, right? Same as this point, the eutectic point. Refer to or not what this means. So it means basically that at this point, this composition, okay, in this particular phase diagram, eutectic point, drop the, what's the composition there? 61.9, they've given you, isn't it? It's written there. At 61.9 weight percent tin, okay, at this composition, it means that once you are dropping the temperatures, you are cooling, you reach 61.9, right? What's the next temperature that follows? Oh. At 61.8 degrees Celsius, what's going to happen? Yes, immediately, instantly to turn to solids. That's why this point in production is very important to us. Okay, it means that our particular component will not undergo this, okay? But it will move directly from a liquid directly to a solid. Are we together? It's known as the eutectic point. This is known as the eutectic line where that is happening. So all those are in your notes. Refer to the meaning. So you have the liquid phase, you have the solid phase. So here it means that anything here is going to, provided it's below 327 degrees, means that any composition here, even 8%, where does it end? Where does that line end? And somewhere about 4. Mine here, sorry, this is not accurate. So if you follow your own diagram, it says 2%, 2.8% of tin. If you picked it from here, it will be just by the boundary there, right? That is what will be running solid form. So it means that this particular solid is rich in what? When you look at the composition, 5% tin, 95% lead. So meaning it's rich in what component? Yes, it's rich in lead. Okay. Because there's more of lead here. So meaning this solid is more of what? Lead than it is of tin. Are we together? Now let's look at this one. Look at the better one here. Comes like this, huh? Pick any point here in between. What would we have? 99%? Let's say 90, 98, not 99. 99. 99 weight percent of what? Of tea. 99 weight percent of tea. What's the composition then of what's the composition or the fraction of lead? 1%, isn't it? Of lead. So what does this mean? This particular metal data is rich in what? It's rich in tin, isn't it? So there's more tin here. Are we getting somewhere? Even tomorrow what? So this means that here our solid phase is rich in lead, and this one is rich in tin. Okay. Same thing. If you run your 99% positioning, draw a vertical line going up. Beyond somewhere here, 232 degrees, that's when it will go into liquid phase. Have you seen that demarcation? The boundary between the phases. That's called the phase boundary. So if you draw a vertical line there with 99% going up like that, beyond 232 degrees there, beyond that point, 233, it's going to run into it's going to become a liquid. Have you seen that? Okay. All right. So now let's come back to our question, original question now. I think now we should be in a better position to answer. That point, have you found your point? You're calling it point what? Point 1, point A, point B? Point A. Point A, in which, the question is asking which phase is that point located? Yes, so now you don't answer solid because you have it's found in the alpha plus beta phase, or in brackets, the solid phase. Okay. Because remember, this is also a, and this is also a. So when you just say solid phase, you can mean anything. It's not a full answer. So it's a alpha plus beta solid phase. Clear? What was the other part of the question I gave you? I only gave you one. Okay. So the question is asking you to find the phase composition. I think let's hold on to that for now. Okay. I just want to make sure that we understand finding points. Let's read the second part of it. Let's come now to the next one. Do we have the silver copper phase diagram? Oh, I have it. Copper, yeah, the next page 2 there. You have the copper silver phase diagram. It looks better now. Hey, now you have a picture understanding. How many phases do you see there? Are you able to list the phases that you can see? There's liquid phase. So how many of them are multi phases? 2, isn't it? Alpha plus liquid and beta plus liquid. Have you seen that it's very similar to the one that we just did? Okay, so the question now. So it says for the following alloys there you had full colon, right? So part B of the question now. 55 weight percent silver. 55 weight percent silver and 45, right? One is 55, the other one will be 45, right? 45 weight percent copper at 900 degrees Celsius. At 900 degrees Celsius. So you have 55 weight percent silver, 45 weight percent copper at 900 degrees Celsius. You're supposed to find the phase for that alloy. Hmm? What's the answer? You found? It's in liquid form. Okay, correct, liquid form. Let's look at another one. What? No, but it's okay. You cannot say just raise it. If you've not found liquids, 55 that you raise like that, right? And then you are 900, where they intersected. So the liquid. So you raise a vertical line and then a horizontal. Make sure that your horizontal lines are parallel to the given horizontal lines. Okay. If you draw a bent one, obviously your answer will be wrong. So meaning in your answer sheet you indicate liquid phase. Yeah, I did not see how you were drawing there. I'm interested in the final answer. How you were drawing and whether your lines were bent, I'll never see since it's because you are drawing from your question paper. Okay. So ensure that your drawings, your vertical lines, your horizontal lines are accurate. Have you understood? Yes, ma'am. Please go ahead. So forget about use the one that is here, okay? Don't start trying to plot for copper. Okay, because the x-axis is showing us composition for what? For silver. So automatically we said it's a binary system. And if silver is 45, copper automatically is it's the same line. Hmm? What? Oh, that's good. Let's look at one more. Let's look at one more. The same phase diagram. What if we have a composition? So let's say silver is at 38%. Okay. And then obviously if silver is at 30, copper will be at what? So at what temperature? Let's pick 800. 800 degrees Celsius. Hmm? What? Alpha plus? Okay. Yes, alpha plus liquid. Right, alpha plus liquid. I'll think about that. So what have we found there? Are we all comfortable? What phase have we found? There's a lot of noise. What phase have we found? Alpha plus what? Alpha plus liquid, isn't it? Have we all understood how we got there? Have we all understood? Okay, so without further ado, let's move to the next phase diagram. I'm slowly getting there. Let's come to the last diagram. Let's come to so what's the zinc copper alloy code? Zinc copper. Zinc plus copper, what does it give us? We're coming here. This was in full-time paper. I think they just ended sessional. Are we there? Are we all here? Yes. So this one has a number of phases, isn't it? How many are you able to identify? So we have beta plus, so we have liquids, alpha, beta, gamma, delta, epsilon. Even have the N one there, isn't it? So we have the number here. Okay. So obviously we know which ones are liquid, which ones are transitional, isn't it? The ones that are molten are the ones that have the L, right? Okay. The solids are the ones that have those Latin symbols, isn't it? Alpha, beta, beta, gamma, and so on. All those combinations, various combinations of the Latin symbols, right? Those ones are signifying the solids. Are we together? So what does this mean? It means that at certain temperatures, zinc and copper will combine to form a totally different solid. Okay. And that totally different solid is what can be gamma, can be epsilon somewhere, and so on and so forth. Okay, so they'll combine to form and undergo a chemical reaction and form a totally different solid that has a different name for it. It's not just alpha plus beta, but that alpha plus beta will go and form something totally what we call gamma at a different temperature and a different composition. That's why you have here this composition is this, and you see that as you increase zinc composition, what happens? The combinations even become more complex. Huh? When the zinc is less, this side is less dramatic. You just have even one solid A alpha, this whole part. But as you increase your zinc, As you go to the right, as you increase your zinc, what's happening at different temperatures? Different combinations, isn't it? Okay, so we're interpreting this now better, right? Making sense a bit. Okay, so now let's go to our questions on this one. Okay. Unfortunately, I wasn't numbering these phase diagrams. I just pasted them here. So you say phase diagram number what? Number last. Number 4. You can give them numbers. You have a pen there. You have been empowered with a pen. Put 1, 2, 3, 4. So you call it number 4. Okay, so phase diagram number 4 is a copper zinc phase diagram. Well, number 4 is a copper zinc phase diagram. So I want to use this again. So I'm not going to erase this. Okay, so for air, 30 weight percent zinc, 70 weight percent copper alloy, make schematic sketches of the microstructure that would be observed for very low cooling at the following temperatures. So very low cooling is also known as what kind of cooling? Very observed for conditions of very low cooling. Oh, sorry, not very low, but very slow cooling. I beg your pardon. Very slow, an S there. Very slow cooling at the following temperatures. So very slow cooling is also known as what? Equilibrium cooling. So there's fast cooling and equilibrium cooling. Fast cooling is when you get that molten state, isn't it? While it's hot, as it just begins to solidify, probably you dip it in water. Not hot water again, in cold water. So obviously the water will become hot, eh? So that happens in the mines. Eh? They'll be dipping in. Who has the time to wait for equilibrium cooling when you've got business to make? Right? So usually in industry, we move with fast cooling. Okay, we try and drop the temperatures using whatever that we can. Usually we use water to do so. Okay, so when that happens, the microstructure that will form during very slow cooling is different. Okay, how the particles, the atoms will be solidifying during very slow cooling is different from fast cooling. I'm sure you can imagine that, isn't it? Right? So the layering that will happen is different. So for academic purposes, we usually stick to very low cooling examples, okay? Because it's easy for us to understand, it's more logical to understand the concept. Of course, when in industry, sometimes they do very low cooling or very slow cooling, sorry, and that happens. So let's look at this question. It's asking us to look at the microstructure. So now, the temperatures, 1,100 degrees Celsius, 1,100 degrees Celsius, that's for A. B, 950 degrees Celsius. C, 900 degrees Celsius. And D, 700 degrees Celsius. 1100, A. B is 950. C is 900. And D is 700. So now let's park this one for now. This one you're doing yourselves. I want us to come back to our first one here. Okay. So the first point we picked, which was the liquid form, which one was this? No, the first one we did was where? Was somewhere here in solid form, 75, somewhere there. Composition. So which was our A form. Then we did another point where? We had another point somewhere here. In the liquid phase, huh? Okay, so now how is the microstructure? So microstructure is what you see when you go under the microscope, isn't it? I must have mentioned that whatever metal, isn't it? When you go under the microscope, you see the boundaries there, right? So now we're asking, what is it that you see? Liquids. When you put a liquid under a microscope, what are you going to see? It's clear, right? So that's a microstructure. Just be, yeah. Those that like decorations indicate that it's a liquid. Okay, so that's the microstructure for the liquid. Let's come to this one here, alpha plus beta. It's a solid, right? So when we assume this is a dish where so it's a solid composed of what? Beta and alpha particles, isn't it? Like that. Okay. What about this point that we had somewhere here? Our point C here. What phase is this? It's a solid phase, isn't it? What solid? Alpha, isn't it? Alpha solids. So now let's come to this question. I want you to find these points first of all. Locate. Let's look at number 1100. You draw the microstructure for that point.
With the 50 weight sensor.
So for A, what's the phase? Have we all found it? So for liquid, draw the microstructure.
So that microstructure seems to be say
You can do a square, but there's no point in being controversial. Just do a circle. I do a circle so you can just follow suit. It can also be a square or even a triangle. Yes, depending on the microstructure. One can be a blank circle. So remember, this is a question. So the circle you're putting it in the answer sheet. Yes. However, you need to know how the microstructures form because it's different depending on the alloys that are involved. So that's why usually I'll pick this form, say study this, not this one. Okay, so let's go to B. B, please. Pardon? Okay, so you have a molten state, isn't it? So how do you draw a molten state? So you have those components, isn't it? The solid components inside a liquid, right? So that's what? Alpha, isn't it? So these are alpha solids. We move on. What have we left behind? We're all working at and moving at the same pace. Okay.